Hello all, this is the second section of the webinar for OpenCall experiment of the ORCA project. In this presentation, we will introduce the ORCA functionalities that are offered in this OpenCall. The first functionality is the concurrent operation of multiple radio access technologies on a single SDR. The functionality is supported on the Zinc SDR platform. The SDR has a wideband radio front end. Each individual RAD is running concurrently, as the wideband radio front end is shared by multiple RADs through the digital down filter banks, like shown here. The baseband processing chains of the multiple RADs are realized and running independently on the FPGA. Two of the RADs that we already support are the IEEE 802.11 and the IEEE 802.15.4. Some RADs have strong similarities among each other, hence part of the hardware modules can be used in multiple RADs, such as the preamble detector, as shown here, that is used both by the 802.11 and the 802.15.4 technology. The second functionality is the integration of PHY with higher layer protocols using a Mac design platform called TISC. So TISC stands for Time Annotated Instruction Set Computer. It is originally designed for sensor platform and has also been ported to run on the ARM processor. So it is now also supported on the Zinc SDR. The advantage of using TISC is that the MAC protocols that were already supported by TISC before are now also automatically supported on the Zinc SDR. So it allows for flexible design and easy switching between MAC protocols. The basic idea or structure of TISC is comparable to a computer. So it has a memory and a TISC core. Various MAC protocols such as TDMA or CSMA and many others are compiled into radio binaries and stored into the memory. So the TISC core loads the radio binary into the core, executes the binary, and also therefore execute the corresponding MAC protocol. There are some dedicated hardware modules such as timer or some PHY transceiver accelerators running on the FPGA to support the execution of the MAC protocol running on the Zinc SDR platform with the TISC platform. So the next offer is about integration of PHY with higher layer communication protocol, but this time running on the NI USRP and the LabVIEW tools instead of the Zinc SDR. Here, the higher level protocol stacks are implemented using the NS3 LTE and NS3 Wi-Fi models as the baseline, as you can see in the figure here. While the LabVIEW communication application of 802.11 and the LabVIEW LTE application framework are used for the physical layers. The higher level protocols are integrated towards the physical layer using a common API. A good example of how this offer could be used in a real-life experiment is the ORCA Showcase 4, which is called Interworking and Aggregation of Multiple Radio Access Technologies. So for more details of this showcase, please refer to the deliverable D2.1 document on the ORCA website. In this offer, the focus is on the lower layers such as PHY control, or lower MAC. The runtime parameterization can be triggered via the testbed or adaptive through a radio resource control layer, as applied for the LTE. Alternatively, a dedicated MAC processor, such as the TISC, as mentioned in previous offer, could be running on microcontroller or SDR onboard processor, ensuring time agnostic and real-time control of lower-level parameters. For the NI-LTE and 802.11 application framework, which are the building blocks for the ORCA Showcase 4, several physical layer configuration parameters are available and can be applied in real time. Examples include the carrier frequency, resource allocation, modulation and coding scheme, or transmit power. So this offer is about coordination strategies between multiple RADs. In ORCA, an NS3-based prototyping platform for the RAD interworking techniques is established using the NI's SDR platform in combination with the NS3 network simulator. Radio access technologies such as the LTE, 802.11 or 5G new radio are considered and integrated into a new prototyping setup for various deployment and test scenarios that have not been possible so far. So the key benefits of using this offer are listed on the right side. The first one is that it allows end-to-end experiments to investigate for scenarios that, for example, are the aggregation and split of the user data. And then it allows for flexible configuration of interworking of different types of communication systems, such as the scheduled versus the ad hoc network. It also allows for programming and configuration using real-time capable SDR components such as the FPGA and the Linux real-time CPU. And then it is also possible to do fast simulation and integration process using the NS3 loopback modes. And finally, the platform is extendable for interworking concepts such as multi-point TCP, low-weight IP, LTE and Wi-Fi aggregation, dual connectivity, or carrier aggregation. In this functionality, we offer the radio slicing. This is supported both on the Zynq SDR and on the USRP devices. Slicing represents an innovative way to support multiple RADs with distinct PHY, MAC, and network features in a common underlying network infrastructure. In this offer, we focus on slicing at the radio resource level. The current development of ORCA mainly supports frequency slicing. This can be achieved by the DDC or DUC filter banks, as shown in the concurrent running of multi-RADs offer. Another way of frequency slicing is through the FFT-based filtering. In this method, different RAD signals are converted and combined in frequency domain using the FFT blocks and converted back to the time domain using a single IFFT block. The space slicing, or in brackets antenna slicing, is also supported by the ORCA implementation, enabling the assignment of different antenna ports to different RADs. The slice in time domain is realized by tuning MAC parameters. So now we move to the next offer, the RAD slice classification through machine learning. The emergence of highly reconfigurable radios and radio slicing poses new challenges to inter-RAD coexistence and spectrum sharing. We believe machine learning will represent an important tool in this context, enabling radios to distinguish different types of RAD slices in its environment and using such information to meet their traffic requirements. We offer a framework and several tools that experimenters can use to create their own labeled RF signal datasets for machine model training and testing, and running different types of model training of deep learning based models for the RF signal classification. So in the distributed massive MIMO offer, we present a complete and unique massive MIMO testbed, which includes two main hardware components, a base station, and up to 12 user equipments. Both components are based on the SDR controllers using the USRP reel from National Instruments. The antennas for the base station managers are the patch antennas. There are 64 antennas in the whole system, grouped into two arrays. Each array contains 32 antennas, and the number of antennas in a group can be configured, ranges from 4 to 8, 16, 64, 32, and eventually 64 antennas. So the two distributed arrays will generate a spatial diversity of the antennas and can be used to multiplex the multiple transmissions concurrently. The distributed MIMO can greatly improve the performance of the system. So in this testbed, the LTE is offered to operate in the TDD mode, and it has a reciprocity calibration to estimate all the channels and power control. For the different experiments, the three types of linear receivers can be selected, being the zero forcing, the maximum ratio combining, and the minimum mean squared error. Eventually, all of these can also be configured. The next offer is a MAC protocol functionality called Sense and About MAC. This offer provides an in-band full duplexer to enable bidirectional communication. As it is shown in the figure here, we have one electrical balanced duplexer in each node, which attenuates the self-interference signal up to 70 dB. This capability is then employed to perform collision detection. In our setup, we have 4 full duplex nodes with the IEEE 802.15.4 physical layer and standard CSMA/CA MAC protocol fully implemented on the FPGA. The MAC is open source, which comes with the sense and abort capability. Through this functionality, the transmitter listens to the channel and abort transmission once a collision is detected, hence saves the energy and improves the overall network throughput. In the last offer of this OpenCall for the experiment, we introduce a millimeter wave system. The system is composed by an access point and a user device, which are equipped with the NI-PXI system. Each device has a 60 GHz steerable antenna attached to it, and it has a list of predefined beams. In this OpenCall, we offer a setup based on the hardware-in-the-loop concept, which measures the channel power of each beam pair between access point and the user device. The measurements will be exported and will be made available to the experimenter. The advantage of this functionality is that all the RF and baseband processing is performed by our equipment, so any further study based on the channel measurement can be done offline in an easy programming language such as MATLAB or Python. With the channel measurements, ORCA allows the experimenter to develop his or her own beam alignment, beam tracking, and receiver algorithms and applications on top of the millimeter wave system working in a real-life 60 GHz channel condition. That will be all for the second part of this webinar. I would like to thank you for your attention.